started. Okay, so welcome back. So I hope everyone is okay for the midterm. Right. So let's start. And I noticed that there are 2 weeks. There are 2 weeks that I need to go to examine students for the administration, master administration interview. Okay, maybe next weeks. And then I noticed another no lectures day will be sport event of an NYCU sport event. So I found that there will be two Wednesdays that we cannot have lecture in the remaining semester. And I calculate that these 2 Wednesday we still need to use video lecture, and then to fit in 16 weeks of the semester. So yeah, I just want to let you know that we have this little bit difficulties here. 中文讲一次，就是我发现接下来的学期里面还有2次会没办法上课。第一次就是我要去面试，硕班的面试，就是让他们就像你们如何进来的时候的一样啊。一个礼拜3，然后下好像再下一个礼拜3又要运动会，全校停课啊，所以说就遇到这2个，那还蛮糟糕的事情是，就之前又有台风啊，放假这样子，所以就蛮多这种需要 lecture 的，就 video lecture，就是还是要上传影片，不然的话16周真的就是上不完。就是我算了一下，就是那2次都要上 video 的 lecture， 然后我才会在最后一个学期考试的那一周给大家考试。所以就如果今天又有一个台风假或放假的话，那就真的是很麻烦的事情了。好的，跟大家讲一下。Another thing is that you notice that I have this really big bag here, and this is kind of a bonus for students in here attend this lecture physically, and these are the gifts because I went several high school, university to give a speech or talks or share. So they typically will give me some gifts, but I think I don't need that. For example, University of Yangming height, right? I don't need that. And the light, photo frame with light, I don't need that. And some really great notebook or even t-shirt and books. So I have a lot of stuff here, and I don't think I need that, but I don't want to throw it away. So now what I'm going to do is that I'm going to give you opportunity to answer my questions during the class, and I will give you bonus, and then you have a chance to select gifts by yourself. Okay, you don't need to choose it, but if you see something you like, just take it away. All right. So I guess it will be another bonus for students here. 听得懂吗？所以我去外面演讲，他给我很多纪念品，那些纪念品有些还蛮贵的哦，还有艺术品哦。但是我觉得我又不需要，然后我把它丢掉太可惜，所以我想说，你们可以在就是课堂间，我就是可能多问一些问题，然后问了问题以后，你们答出来，你可以加分，然后你还可以自由选择东西在这里啊，就随便选啊，你爱什么就选， 就是你有兴趣的话，等一下下课可以来看一下。就是你觉得这个我想要，等一下下一个人就赶快去抢答，然后就可以来拿这东西这样。那下课的时候你可以来看一下，OK？ So I just saying that if you are curious about what the inside, you feel free to come here during the break, and then you can see which gifts you would like. Well, I guess this is not really good. I guess it will be end up sort of way. Anyway, so you can see that good or bad gifts here. Books, very nice book, very good friend of mine. So yeah, so later you can feel free to take a look. All right. Then I'm going to okay. So let's continue our lecture. So last time we talked about the difference of kinematic and kinetic, right? And then kinetic means that we're going to talk about the atoms or particles inside a system, and then how they move, and what is kind of velocity, and how they bump to each other, so and how they go through certain areas. And then all these things I mentioned above are related to the material properties of that system. All right. And before we enter this kinetic theory, we are going to assume several conditions that otherwise we cannot go forward. Okay. So first one, we are going to assume that we have large amount of particle or atoms in the system. And then we say this is correct, and this is suitable, really fit in the fact. Okay. And also the second one is that they are separated at least 10 times of their diameter. Okay. And then finally, not finally, the third one is that no forces exist between molecular. So they won't see each other except they are bumped to each other, collisions. Okay. And also we assume that they bump to each other before in between each collision, each bumping, no duration time, because we assume that moving so fast. Okay. They are moving so fast. So we assume that they bump to each other in between their no duration time. Okay. And we kind of measuring how frequent they bump to each other is that the average distance between each collision, which means that it's called mean free path. So which means that averagely the particle will travel such distance to bump to next one. Okay, so that's the assumption. So here assumption is that no duration time because they move really fast, and we just see how frequent they bump to each other by using mean free path. And then the fourth one is the collision are elastic. Momentum and mechanical energy are conserved. Well, I believe it is a little bit easy, right? We assume the perfect bumping, perfect collision. So perfect elastic, nothing changed before and after the bumping. No energy loss. The fifth one, the molecular are uniformly distributed with a container means that there's no preference corner for atoms. Okay. The sixth one, the direction of the velocity of the molecules are also uniformly distributed. Okay. Right. So the direction of the velocity has no preference. Okay. The atom has no preference for the direction they are going to move. Okay. So this is the sixth fundamental assumption for kinetic theory. 好，我们讲的就是我们假设它非常的atom 之间是没有力量的啊，它就纯粹就是你给它一个能量，然后它就开始动了啊。然后我们不考虑它们之间力量有没有吸引力交互作用力，没有，它们就是飞来飞去就对了，一堆乒乓球在那边动来动去，在系统里面。然后呢，我们假设它非常的快，动得非常快，就互相撞击。那他们没有撞击的时刻，他们就没有看到彼此。OK， 然后我们不考虑他的跑的时间在两个撞击之间，我们都不考虑它经过多久。总之，反而我们用的是另外一种方式去计算它的碰撞的频率，其实是 mean free path， 也就是平均的没有碰撞的路径。它平均走多长的路才会撞到下一个 ？OK。然后第四个假设是我们假设它是完美的碰撞啊，它的动量跟能量都完全守恒。第五个就是分子或是 particle 颗粒在这个系统里面是uniform 就是均匀的哦，就是没有任何的偏好啊，它都是同样的几率。然后第六个也是它的速度的方向也都是没有任何偏好的，都是同样的几率。OK， 有这六个假设，我们就可以去开始看它的去看它的那什么 kinetic energy kinetic theory。Okay, so let's sort of discuss the particle. The kinetic we discuss is kind of fundamental, it's kind of ancient, 19th century things, 19th-20th century things. How about nowadays? Nowadays we use molecular dynamics because previously, obviously, we cannot calculate all the atoms movement, so we cannot consider the force between them. But nowadays we have powerful computer. We can use molecular dynamics, 分子动力学 molecular dynamics, which can calculate the force or interaction between atoms. So it becomes possible. It's a molecular dynamics is kind of more advanced numeric solutions for simulating materials. That's what we are doing right now in our lab in Professor Luo Youjie 老师 lab. Okay, so we can introduce how they. So this is not really important in kinetic theory because this is kind of more advanced. Okay, so we just introduce the latest techniques. Okay, the simplest potential. The potential means that the molecular dynamics simulation considering the potential between atoms. Okay, so the most simplest potential here is Lennard-Jones 612 potential. What is that? This is kind of really typical simple potential in molecular dynamics. We call MD molecular dynamics, MD simulation. Okay, in MD simulation, for example, the particles with the radius and also the distance between them. So the r is the distance between them. Okay, and we discussed that before, right? We have a typical van der Waals and electrostatic repulsion in nature between two atoms, right? Van der Waals, they will attract, but the electron, they will kind of repulse to each other because they have the same sign, right? So they will repulse to each other. So the blue one is the repulsion potential, and the green one is the attraction potential. When they sum them together, they will have such shape here. Okay, so when they summed up, there's this shape. We introduced maybe next a previous PDF, right? We said this is kind of the energy well, and then if you want to separate, then you need to overcome this energy well. We discussed that before, right? In the next previous few weeks. So in the computer, we typically using a really simple formula. Tell the computer saying that if you just give the computer two parameter. What is a parameter? This value and this two value. With this two value, dr and delta E, with the two value, it can simulate different type of material, different type of atoms. So when we assign these two parameters, we can put that into the computer, and then they can calculate how each atom move. OK， 好，我们要讲的就是前面讲的是 kinetic， 就是动力学，好，动力学。但是那个动力学它是古早的，古早的人没办法算出所有的 atom 的移动状态，所以它只能假设没有 force， 但实际上它们是有 force， 它们之间是有交互作用力的。那所以说现代可以了，现代我们可以使用超级电脑去算两个 particle 之间的交互作用力。那交互作用力最简单的一个势能叫做 Lennard-Jones potential， 我们可以使用分子动力学去用超级电脑，然后告诉超级电脑两个 atom 之间的势能长什么样子。那我记得我们在前几个礼拜有讲过两颗原子很典型的势能之间的势能可以被这样子的曲线来形容，对不对哈？那这两个式子，这条线可以用很简单的式子就可以表示了，只要有两个 parameter， 两个参数，告诉电脑，它就可以去计算两个 atom 之间它的距离的时候，它们之间的交互作用是多少，它的势能位能是多少，就可以去反算出它的真实的速度，有考虑到力量的速度了。OK， 所以说 MD 就是分子动力学 molecular dynamics， 比 kinetic 更前瞻，就是更现代化、更厉害了啊。那这就是我跟罗杰老师都有在做的东西。那就可以跟实验一起去相辅相成这样子。All right, so this is one of the application. For example, nanoparticle drug delivery. Okay, so this is a kind of scenario that the patient has cancer here, and we can get the drugs here and then covered by some PEG or other stuff and make it as magnetic properties, and so it can guide by the magnetic field, and the drug won't hurt other good cells of your body. Okay, and how to how to simulate that, we can just make the particles, this is drugs, and this is the PEG or polymer, and then we put them together and to see how they interact together. Okay, so yeah, this is a typical molecular dynamics, really simple one. It's just example. Without polymer, with polymer, and you can see that if the polymer, without polymer, the particle will aggregate together because the van der Waals and van der Waals potential attraction. And but with the polymer, it can has a proper radius of the drugs. Otherwise, this cannot be guided by the magnetic. Okay, so let's try if I can see that. Yeah, here. Okay, this is a particle with polymer. So the polymer, the blue polymer can stop them aggregate too much. Okay, and you can see that each atoms are calculated so they can move properly. But in ancient like 19th century, it is not possible for humans to calculate every atom's movement. All right. And next will be no polymer. So they will aggregate together and become a not nanoparticle. And then it can become bigger and then it is not controllable. Okay. Just like a movie, an interesting games, 3D games. Right. Alright, so 所以我说就是有了 MD，我们就可以去应用在新型的东西上，例如说纳米的药物释放，这边有一个癌症病人，然后他的这边有癌症细胞，然后我们就使用药，然后搭配一些高分子，然后这些高分子可以让这些药不要过分聚集。如果纳米的颗粒放在一起，绝对变成一个微米颗粒啦，因为它会聚在一起，所以我们必须要有分散剂。然后这个分散剂如果弄得好的话，上面有磁力的话，还可以把它引导到对的地方，不要去杀好细胞。然后这边就是一个很典型的例子，刚刚播放的影片就是说，如果有高分子的话，它就会挡的比较好，它就会变成还是 nanoparticle 的 size。但是如果今天不挡好的话，它就会过分聚集成为一个大的。那这个东西就可以帮助我们跟实验配合。So we can cooperate with experiment group and to give them some guidance and the direction of the experiment. All right. Now let's go back to the ancient stuff. We need to understand ancient stuff, and then we can improve ourselves to the more modern technique, right? So now let's go back to kinetic, the ancient stuff things. Let's see how ancient, smart scientists, how they dealing with these things without good tool like us. Okay, so randomness of the motion. We are going to imagine that the container has many particles, and all the particle has its own velocity. And just like human, just like a society, we have really fast atoms, and we have really slow atoms. But most of the atoms are in the most probable speed. So this is kind of the distribution of the atom's velocity. This is not normal distribution. This is it will affected by their properties, and also the property of the material and the condition of the system. But typically it will looks like this. Okay, most probable speed, and then higher speed has lower population. Really low speed also has lower populations. Okay, so we can draw this picture, and we say this picture is probability density function. Density function. Okay, density. So this is not probability. This is a density. Sorry, this is not probability. This is probability density function. So, you know, probability has no unit, right? But what is the uh, uh, what is the probability? It actually is the, well, it actually is the area it covered underneath by this curve. Okay, so we call this curve F nu, sorry, FV, sorry, FV. The FV here has a really important definition. FV dV integrated from 0 to infinity become 1. Okay, no unit. So here I will give the 1 pink color. Okay, pink color. They need to be correlated. 1, all the area underneath this curve is 1. Okay, all the velocity. And of course, there's no unit. So here, this is 1 is probability, right? 1. No units. So you can see that FdV after the integration is no unit. So probability density function is actually unit upper inverse of V, because you need to integrate the V here to get no unit, right? So your probability density function is so your V is actually M over S, right? So your F nu, sorry, FV has the unit as M. Okay, so inverse of velocity. So that after you integrate it, and then you can have the probability itself. So if you understand this, now the blue part here, the blue part here is the fractional number of molecules in the speed range between V to dV, V to V plus dV. So this blue region is the fractional number of the molecules in the speed range of V to V plus dV. So here is the probability that you choose from the particles in the container, and that particle has the velocity within this range. Okay? Right. So if you can accept this, you know that after you do the integration, you can obtain the probability or the chance has that kind of velocity, right? After you do the integration. So it can help us to determine mean speed. Okay, the mean speed, how can we determine the mean speed? Easy. Mean speed is defined by 0 to infinity and V times FV dV. Okay, what does that mean? What does that mean? It means expected value. Okay, 期望值. Remember that during your senior high school, right? If you roll the dice, your expected value is 3. I don't know. Anyway, so you know that expected value, right? So you can see that this is the velocity times its own probability. Okay, and summing out together. This is expected value definition, right? So v times this, good. And then mean square speed, easy. Mean square speed, the definition is 0 infinity v square fv dv. Okay, so very similar to what it looks. VRMS, rule mean square speed. So basically is the v square mean square speed and took the square root. And nth moment of the distribution, wow. Just give the terminology. It's not really important. All right, so maybe you may ask why we are going to need mean square speed, because we are going to determine later, we're going to determine kinetic energy, half mv squared, right? So square, v square is really important for us. Later, we will use that for determining kinetic energy. All right, so that's it. 好，那我们现在要讲就是要看回到动能学，是古代的动能学，不是现在的分子动力学。动力学不是现在分子动力学，是古代的动力学。那它是有点类似像统计的方式，哦。那他画了一个图，就是我们可以知道，在一个系统里面，超高速的 atom 是很少的，超低速的 atom 也是很少的，但是平均速的速度的 atom 就比较多，就跟我们的社会一样。那所以它就会画出一个这样的东西。这条线我们叫它 FV， 这个 FV 叫做 probability density function， 不是 probability function 哦，它是几率密度函数。也就是说，它必须要去积分了以后，它才会变成它的几率。OK， 那再讲简单一点，就是你把全部从0积到无穷大的这个速度，它的面积会是1。OK， 所以粉红色就是加总起来就是1。那这样的可以表现出来，就是说 FV 它不是几率的单位哦，因为几率是没有单位的嘛，哦，它是积完分以后才有几率的单位，所以它是几率的不速度的导数，因为它跟速度去积分嘛，对不对哈？所以它导完，它是它是导数的单位，单位以后跟 v 积分才会得到无单位的东西的几率。OK， 那蓝色的意思就是说，你随便挑选一个 particle atom 从那个系统里面去看它，这个系统的这个 atom 你挑选的，它的速度正好在 v 加底 v 跟 v 加底 v 之间的话，的几率会是多少？就会是这蓝色的面积。OK， 好，那这个做的要干嘛呢？它可以告诉我们，mean speed 平均速度跟 mean square speed 平均平方速度。OK， 这是干嘛用的？这个平均速度当然没问题嘛，我们要知道这个系统它平均速度，那怎么算呢？就使用我们高中学到的期望值，也就是它这个值乘上它出现的几率，全部加总起来就是你期望值是多少。所以你的体积不是讲错了，速度乘上 FV 比 V 就是，然后再做积分，也就是说这个东西是它的几率乘上它当下的速度，然后积分起来不就加起来嘛？好，就变成期望值了。那平方的话，那就是对啊，就平方加中间，然后 root mean square 的话，就是再开个根号就好了，开个根号就好了。然后 n moment 的话，其实我觉得纯粹只跟大家介绍一下专有名词，把 n 写上去的话，这边是2啦，这边是 n。那可能同学会问为什么要2？因为它叫什么？等一下要算的是动能 ，OK？ 2/mv 平方。Okay, now this is a little bit difficult here. Okay, in the textbook, the figure is terrible. Okay, you don't even I read that book, I don't understand what it's talking about. Okay, so that's why I redraw it in the more stylish way. Okay, more looks better, right? Good looking, right? So let's talk about molecular flux. 我的意思就是说啊，课本上这个图啊，写的有够烂的，画的有够烂。我当时我自己看我都看不太懂，所以我现在把它画成我觉得我自己看得懂的状态，然后我觉得会帮助你看懂它干嘛。All right, so let's talk about molecular flux. Later you will know why we're going to determine this molecular flux. Okay, the molecular flux, the definition of the molecular flux is that the number of molecules from striking a unit area per unit time. Per unit area, per unit time, the number of molecules bump to that area. Okay, this is really important. So if that atom bump to the area, which means that if the area is just a space, nothing there, it will penetrate it, right? Travel through that area. So it's called molecular flux. Okay. So the number of molecules from striking a unit area per unit time, I will give you a unit area. I will translate for you by mathematic symbol, the A and the T. Okay, so the phi, I guess, its definition is the number of molecular, the A, the T. So this is the definition written in mathematic form. All right. So you can imagine that this area, okay, this area is the A, right? And you can imagine that there are many, many particles in different direction. Okay, and also you notice that the arrow I wrote that I draw it has different length, which means that it's a really fast, middle fast, they're really slow and really slow, middle speed. Okay, you can see that they has different direction and different speed. So the number of molecular from striking a unit area per unit time, including all direction, including all speed, right? But it is too difficult if we directly consider all direction, all speed. So now, how about we consider one direction and one speed for now, okay? For now. So we just consider the velocity in this direction, okay? All right. And we just consider the speed, one speed, this v, okay? So now we put this here, okay? So here we only focus on one speed, one direction, all right? And later we will consider all direction, all speed. So now this is our, this particle is our main characters. We focus on that. And you notice that this particle will travel to there, to touch the dA, the striking the dA. How about, and it is v, they have the velocity v, okay? So you can imagine that during the dt, what kind of atoms will hit the dA? This one is possible to hit dA. This one also okay. How about this one? No, because if this particle is here, okay, if this particle is here and they travel v and within dt, it can only travel to here, right? So the only possible atoms that may hit the area within dt is in this cylinder. Okay, outside this cylinder has no chance to hit the area in dt. Okay, so atoms need to be in this cylinder. So what is the cylinder of this? What is the number of cylinder? What is number of molecular in the cylinder? Number of molecular per unit unit volume is that we have the number of molecular per unit volume, n under bar. We named it n divided by v because we assume that particles are normally uniformly distributed. So n divided by v is the number of molecules per unit volume. Okay, so we give the n under bar. So n under bar times the volume of the cylinder will be the atoms inside this cylinder. All right. Right. So and also you can notice that, oh well, later I'll discuss this later. Okay, so the number of molecular with speed v, speed v, 2v plus dv in the cylinder is n under bar times the volume of the cylinder and times fv dv. All right, so that's how we write down this. So n divided by v times fv dv times, okay, volume of the cylinder. What is that? v dt cosine theta dA. Because you see this direction, because this direction, okay, with this angle, right? And from here to here is v dt. So the atoms here just travel dt to just touch this area. So this long length times its direction theta. So you can have its own height. Height times dA will be the volume of the cylinder. Okay, so v dt cosine theta dA will be our cylinder area. Right. And you notice that you take some irrelevant atoms into account here. You see, although these atoms inside this cylinder, but they may not travel in that direction. They only travel other direction. They travel other direction. So which means that only a few of these molecular are traveled toward the A. Only blue one will travel toward the A. The rest of the gray one are not going to hit that. So we need to take that out. Okay? So here we consider too much. We need to times a factor. We need to times a factor. And this factor is belong to this ratio. Not this ratio. Outside of this ratio of this grade, we need to take away. We don't want to take it into account. So we need to consider a ratio. I don't know, 20%, 30%. I don't know, but only the percentage of this atom travel toward that direction will hit this dA. Otherwise, it will go other way. All right. So, and also FV/dV, you know that we have learned that before, right? So, in the next page, I will give you we will continue this. All right. Oh, sorry, I forgot to write down this height. The height is cosine theta v dt. Okay. Right. So I guess I need to give you 20 minutes break, and then if you have interest in the gifts, you just come here. Thank you very much. Wait. Hello, welcome back. I feel sad that nobody has interested with the was interest, but not interesting in those gifts. I'm so sad. Okay, so in the previous hour, in the end of the previous hour, I discussed the molecular flux, right? Molecular flux, and we consider the number of molecules from all direction with all speed while striking dA within dt. Okay, but it's too difficult, so we just consider one direction, one speed. All right, so one direction, which means that all the particle within that cylinder will hit that area because of the dt limitation. And then only one direction is considered, right? So these gray atoms won't hit that area. So which means that the number in the volume of the cylinder is not going to all the often hit that area. So we need to times a fraction times a ratio of the value. Okay, maybe 20%, 30%, 50%. We don't know that yet, but it needs to be reduced a little bit. So we're going to determine what is the blue question mark is in the next page. All right, this is what we just finished in the last hours. All right, 中文 Chinese 分子流量很重要，等下会用到很多。它就是表示说，它的定义就是有几颗原子会在单位时间之内撞到单位面积上。OK， 那这个是所有的方向跟所有的速度都要考虑进去哦。好，可是太难了，所以我们先考虑一个方向一个速度就好。好，那一个方向的速度，一个方向跟一个速度，就这样，这些 atom 啊哈，只有可能在这个形状里面，才有可能在底 t 之内撞到底 a。原因是因为如果它超过的话，它底 t 在这个 v 的速度下，它不会撞到这里啊，它不会撞，因为它来不及撞到底 t 哦，然后如果今天是另外一个方向的话，也不能撞到。但是呢，我们先讨论，就是说，在这个孔子里面，它才有可能会碰到它。OK， 所以呢，孔子里面有几颗呢 ？n 除以 v， 我们假设它是均匀的分布嘛 ，n 除以 v 乘上它的体积就是它里面的颗数了。好，那这颗数也不是全部的颗数都会撞到它，只有某一些方向，只有这个特定方向才会撞到，其他的方向都撞不到。OK， 所以说，我们必须乘上一个问号的比例，可能是20%，是这个的，就是这个方向是占据这全部里面的20%，有可能，但是我不知道。好，等一下我们再算出来这个东西，下一页就要算这个东西。All right, that's it. Next one. Continue. So we assume that the direction of the velocity, the sixth assumption, okay, the velocity of the molecule are uniformly distributed. So all the direction are has equal chance. All right, have equal chance. So which means that we can using the sphere ball. We can imagine that this is a speed space or speed well. All right. We see that this particle, the blue particle, may has many directions. This one, that one, that one, that one, that one, that one, blue become a sphere. All right. And yeah, and we are considering one velocity, right? So this is v, 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 v. So this is a ball, This is a ball. Okay, the ball here. So this particle has such many possibility of the direction, but only one direction here is what we are focused in the previous page. So what we're going to see is that we need to obtain the surface of all the direction, which is a ball, and then consider only one tiny dA, which represent that direction. Okay, so we need to consider the ratio between this dA and the entire surface of the sphere. All right. So how to calculate the surface of the sphere? I believe when you your calculus has taught you how to determine that. Okay, theta v. And this is phi. Okay, so this is v, which means that this is v sine theta. So what is that? Actually, we are going to let you know how to determine this okay, d sigma. Okay, this d sigma is actually d sigma. All right, and I guess everyone understand what I'm talking about, right? Because you have learned that during the calculus. Here is v d theta, and the length of this is v sine theta d phi. I guess you can understand what I'm talking about, right? So this is the particle, this is the particle, and the v here, v sine theta here, and v sine theta can open this arc, right? Open this pizza shape, v sine theta times d phi. Well, sorry, I should say d phi here. It should be d phi, and d theta. All right, should look like that. So that's the d sigma. The d sigma is actually the small red area of that sphere. Sorry, the v sine theta d phi times v d theta, and equal to v squared sine theta d theta d phi. All right, so red area d sigma. So d sigma with and rotate every direction to become a ball. Okay, so sphere integration. It looks like you need to do the theta first. So you can see that you do integration. Okay, this is half minus pi. This is positive pi. So you can imagine that we have a integration and then integration. All right. Now I'm going to give you a bonus chance to win the bonus and also the bonus point and also the gift. So this is okay? Is that okay? Oh, sorry, I can finish this. So minus half pi integration from here to half pi, positive half pi, and then 0 to 2 pi. So it makes a sphere area shape. Okay, so now I'm going to ask you, is this setting okay? If okay, well, if you think this is not okay, please tell me the reason. If this is okay, anyone? 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 Do you think this is okay? Bonus and gift. Raise your hand, come on. I can tell you not okay. And the reason is why. Please tell me. If you can tell me, you have bonus and also a gift. Anyone? Anyone? This is not okay. Why? Minus 2 pi to positive 2 pi. Is that okay? Imagine that this is sine theta. Anyone? 加油啊！听得懂我的问题吗？其实这是不 OK 的，这不行的，这不能是 half pi minus half pi 到正的 half pi，不行。为什么？为什么 ？Tell me why。然后要怎么样解决才行？哦，有人吗？拜托。然后如果不这样做的话，会怎么样？有没有啊？加个分吧，拿个分数吧。哎，好好，哎，不好意思，你们两位，好，你们一起回答好，没关系啊，反正我有很多题，很多那个那个，好，请说，会怎么样？会抵消，很好，你也是这样觉得吗？对不对哈？很好，答对了，上半跟下半会抵消。要不然一个人讲中文，一个讲英文了，你讲的中文，你讲的英文，cancel each other become zero。好了，OK 啦，好，谢谢啦。那两位可以上来这边选一下那个奖品，两位都可以下来，然后顺便来写一下你的那个叫什么学号，OK，下来吧。好，我现在趁现在写一下。Right, the answer, their concern is correct because when you do the integration，仔细找，很好啊，我觉得都还不错。Okay, the integration half minus and positive will cancel each other, so it will become 0. But it's not. Okay, it should be 0, and it should be double. All right. So you should integration from here to here. Okay, and then double it. So this half, and then it will be 2. Okay, and then you can get the real result. 4 pi v squared. All right. The reason is to avoid negative area. Right? 不错吧？不错哦，不错哦。好了吗？哦，好耶，好耶，来，写一下你的那个 2个全号再写在这里，谢谢。来，我们看的是什么？口袋保温杯，恭喜你！
谢谢。
啊，这个书是我的朋友他写书，好，谢谢，希望你 enjoy。谢谢2位，
谢谢
，Thank you, thank you. It's great. Yeah. All right. So, if you can set that 4 pi v squared, and then you can notice that 4 pi v squared.
老师，你好像按到静音了。
不好意思，什么时候没声音的？已经很久了吗
从那个 V square 那边开始。
？V square，哪里是 V？哦，你说这里吗？Sorry，应该还好啦。哦，那应该我觉得整个画面就算是应该都听得懂了哈。OK 的，加油。I hope you can understand. Sorry, I don't know why it become mute automatically. I don't know why. I didn't push any button. Right，讲中文是不是？我刚讲哪里了？总之就是我们刚刚说4派 v square，是怎么来的呢？是从这边积分到这边到这边，可是问题是不行，我不能从2/4负派积到这里，因为它会负的面积、正的面积加起来反而会抵消掉，所以如果你真的这样做的话，这边会是0，但是这样不对的，所以你要是2/4负派到正派，然后乘上2倍。这样它才会真的不会有负的面积产生。好啦，得到一个球，那个球的面积就是所有方向的总和。 那一个小面积就是那一个方向，所以当然我们的这个问号的 vector 就会是4π平方分之底 sigma， 就是上面这个东西，然后删掉以后，这就是第一个方向的比例跟全部的比例这样子。Okay, so now, so this one we got it, and then we can put that to here. All right, so this one is the blue highlight, the question mark. We just named it. So the number of molecular in the cylinder at the time t traveling with speed v plus dv toward dA is this one. All right, and so the definition of the particle flux, molecular flux, is dm divided by dA dt. Luckily, dA dt. Okay, so our dn, our d define 吗 ？define our define the flux is defined by dm with divided by dA dt, and then we can do the integration. So what is the integration? So we put this n and 4π and fv dv and v and cosine theta sin theta cosine theta d theta, and we again this is one direction, right? And then we need to one velocity. So we have all the velocity. Okay, we need to consider all velocity here. All velocity. All right. So this is the figure meanings here, right? We only consider that one, but we need to yeah. So this is all velocity, and this is all direction. All direction. So previously, when we had considered one direction, one speed, now we need to consider the entire things, right? Entire things is all velocity 0 to infinity. Consider all the v, and then your the theta define molecules in one direction. But now we need to make it all the direction. But because because we only talk about the velocity is considering positive and negative velocity. So now the direction we only consider half. Okay, because if you have this integrated, when you do the all velocity, which also means you integrate that direction. All right, so all direction, all velocity by using 0 to infinity, 0 to pi, and 0 to half pi. Only half sphere. Okay, after we done the integration, this part is v over bar, and this part is pi. So luckily, everything is really simple. 1, 4, n on the bar, v. So this is molecular flux. 好，讲中文啦。那刚刚的蓝色的已经讲完了，也就是说，我在这一个时间，就是在单位时间之内，它要撞到那个area 底 A 这个 area 的地方，会有几个底 n 会去撞到它。这个底 n 呢是在它的速度是 v 加底 v 这个区间之内， 跟它就只有 θ 跟 phi 这个方向，就这样而已哦。这是方向，这是速度。one direction, one speed， 这样 OK。好，那这样算出来以后呢，我们就去算它的 flux， 把它消掉以后呢，这剩下的就要去做积分。不要忘了，我们这边是只有一个方向一个速度哦，所以呢，我们的一个方向一个速度要怎么样算呢？我们要把速度 o velocity 0到无限大嘛，对不对哈？那0到无限大，然后还要做就是这个积分。那我们考虑到就是说这个速度的方向，这是 sphere， 它是就是只要去碰到它就好了，只要碰到它就好了。那我们就我想一下 ，all direction 是 g 0到2拍，然后0到2分之拍，然后再积一个圈圈这样子。那为什么不是2分之负拍啊？那我想想看，10拍，有人知道为什么不是2分之负拍吗？就是或者是2倍嘛？为什么不是积全部？我现在忽然脑袋有点宕机了，有人可以知道吗？如果有人知道的话，再继续加分，然后可以送礼物。如果不行的话，我就是下课我自己再想一下，或者回家想一下，我再告诉大家为什么不是。为什么它不是积全？为什么不是2倍？为什么不是圆圈 ？Striking direction。好，没关系，我再跟大家想一下 number of in the 看一下，等我一下。number square 好，没关系，我再想一下。有没有现在要回答这个问题？为什么它只要记一半就好？我这时候我忽然忘记了。I thought it should be double all the direction to touch this, but why it's only half of it? I forgot why. At this moment. So if there's nobody to answer that question, I will go back during the break and or I'll go back to home to think about that, and I will give you the answer. Okay, when this memory go back to my head, sorry, but actually， 好，总之就是所有的速度跟所有的方向积完以后，这边是 v bar， 这边是拍，好，得到一个很简单的东西。OK， so I'm sorry that I forgot why only half of it. I forgot how to explain this. I'm getting older now, aged. Anyway, so accept for now, and I will give you the reason by tomorrow. All right, right. So 所以我中文也解释完了哈，就是我忘记为什么它不是全部了，因为它只要记一半就好。然后我忘记为什么理由了，这绝对是正确的，因为我当时想完以后，我就画了一个半球，但是我忘记原因是什么，下次我要把这个原因注记在上面，免得我会忘记。OK，Anyway，然后如果同学没办法回答我的话，那我等一下下课看一看，或者是我回家再看一看。我明天之前会跟你讲为什么。Alright, sorry. So now the flux is really important. Okay, it's really important. It can help us to get pressure, gas pressure, because when you imagine that pressure is actually caused by particle bumping to the wall of the container, right? So the wall when they bump to the wall, actually you can imagine that this is the A and the atom striking on dA during dt, right? So they are exactly what molecular flux means, right? So the change of that's okay. So the definition of the pressure is equal to dP over dA dt. The dP is the momentum. Okay? The momentum. Okay, you see that the dp here is momentum. The momentum is small p. Sorry, there are two p here, capital P and small p. All right. So you can imagine that the change of momentum of one particle during the bumping to the wall is that you see mv bump into the wall and bounce back. Okay, and you can see that the direction here the component of this okay, you can see that when you bump to the wall and then come back, the only change of the momentum is the red part. The blue part doesn't change. Go to the right hand side, right? But the bumping, the red here, is a change of momentum. So the change of momentum is mv cosine theta minus mv cosine theta. You see, if this is a positive and this is a minus, you change 2mv cosine theta to make the positive one to become negative one momentum. Okay, so the change of momentum is 2mv cosine theta. I hope you can understand this. And then the change of momentum produced by all the molecular with speed v2 v plus dv toward dA in the time dt is all right. So here it's wrong. It should be the small p. Okay, this is momentum, a change of momentum. So change of momentum for all the molecular. So you can see that this is all direction. The integration means all direction. And the n here is one direction. The red one direction. What is the n? You just learned that in the previous page. F underbar fv dv times v dt cosine theta dA. Wow. 4 pi and sine theta cos d theta d phi. Okay, so wow, your dn looks like that. You learned that in the previous page. All right, so after doing the integration, 0 sigma 0 infinity 0 2 pi 0 2 pi, sorry, 0 half pi 0 2 pi. After that, you can say this is v square bar mean square speed and 1/3, and this is 2 pi. So you got 1/3 m bar n on the bar mv squared dA dt. And n on the bar, you know that is m divided by v because all the number of particles are uniformly distributed in the container. All right, this is important. Okay, so dP looks like this. Pressure is dP divided by dA dt. Luckily, we can cancel each other. All right, so our P equal to this one. Okay, and we make the V go to the left-hand side of the equation. We can have PV equal to 1/3 mv squared bar. Okay, and we can say 2/3 half mv squared bar. So what does that mean? This means that 2/3 average translational kinetic energy. Okay, so that's 2/3 times the average of translational kinetic energy. Right， 好，我们刚刚算完 molecular flux，OK， 然后我们就可以把它拿来去算一些我们平常知道的东西，其中一个就是 gas pressure。gas pressure 我们都知道就是 particle 撞到容器的墙壁所造成的气压嘛，对不对？哈，那它的定义就是 pressure P 会等于它的 momentum change 分 dA 分之 dT。dA dt 的分支 momentum change。那什么叫 momentum change 呢？就是这个，你想象一下，它的 particle 撞到这个墙再回来，它改变了什么？它改变了去跟回，但是又没变哦，又没变，所以真正改变的是去跟回。原本是去，如果是正的话，回来就是负的，它改变是2倍的量。OK， 所以 mv cosine theta 要2倍，2mv cosine theta。好，这就是它的撞一颗球撞到一颗颗粒撞到墙壁所改变的动量，但是气压是所有的方向、所有的速度，所以我们要重新再做积分。所以我这边写错了，它是大 P， 我们应该是小 P。change of momentum 改变的动量呢是全部的哦，是 all direction。那我们刚刚讲过，我们的 one direction dn 是这样子的东西，是前面那一页我们算出来的嘛哈，然后把它带进去。算就发现它是长这样子。那这个只是底 P， 把 dA dt 消掉以后呢，我们就可以得到P 是多少？但是这个 N 又等于是 N 除以 V 嘛哈，所以我们把 V 移到左边去以后，我们 PV 就等于1/3 mv squared bar。那我们再发现，如果直接把2就是分开来看的话，这边正好是动能呢，正好是动能。好，那就所以是2/3的动能会等于 PV。So it can help us to get some ideal gas law, and as you can see, PV equals MRT and equal to NKT. So this is what we learned. We already know that, right? So K is Boltzmann constant. That's common sense, right? For ideal gas, NKT equal to the one we just obtained. So 3/2 KT equal to half mv squared bar. And then I guess I need to give you a break. So I will see you after. 没有11点，还有10分钟嘛，对哈 ？Sorry. Okay, we can continue. Sorry. Right. So let's continue. At room temperature 293 K, if we substitute this into that, we can have this value, and this value is kind of averagely room temperature standard condition that the kinetic energy look like. So actually, it will remember this R, VR, right? Do you remember this curve, this potential curve? Typically, this energy well is in the range of this 0.03 AeV. So which means that typically you need to provide such kinetic energy to let two particles to separate them to overcome this energy well, so they can fly away. All right. So this is a typical potential well is in the range of this. All right. 好，我们就刚刚得到的就是我们的particle 跟我们的 particle 的运动跟我们的 pressure 是有关系的。那我们就可以把它连接到ideal gas 借由这个 P 之间的关系。那 PV 等于 MRT 跟 NKT 这个我们之前都知道了哈，波兹曼常数，然后我们刚刚算出来是这个东西。那刚刚算出来这个东西呢，我们看看真实状况大概会是多少呢？我们就把真实状况 room temperature 带进去，我们就可以得到一个数值 0.038 eV。好，这个数值呢，大概就是在就可以克服就是 atom 之间它们的交互作用力的这个 energy well， 就是它那个能量井啊，如果能把那个能量井克服，它就可以飞走了，这样的意思。Okay, so now next one, let's go into next things we are going to introduce in kinetic theory, which is molecular degrees of freedom. So in the molecular typically we talk about two atoms connect together. So you can imagine that there are several possibilities for they to move. For example, translation. Translation is easy, right? Just moving. This is molecular. Okay, this is molecular. Molecular, you can imagine that they're connected by the spring. All right. So molecular means more than two atoms, right? So we consider two atoms connecting together. They can be moving along X, moving along Y, moving along Z. So translation is a degree of freedom for that in space. Okay, motion of the center of the mass. The center of mass can move forward, backward, left, right, and up and down. So 3 axes. Another thing is rotation. So this stuff can be rotated along several axes, and we will explain this later. And vibration, of course, the particle between each other may vibrate during the temperature, right? If you have the kinetic energy, I mean heat, it will be heat vibration. So vibration is just vibrate with relative to one another. Okay, so this is degree of freedom. The molecular can move, right? 那现在讲中文就是分子，我们要讨论刚刚讲颗粒嘛，哈，但是颗粒就只有一颗，其实不太 general， 不太一般化。其实我们真正有时候会考虑到的是分子，分子就是2颗以上。那我们就先考虑2颗了哈。这2颗呢，它的自由度，移动的自由度有以下3种类别。第一种是移动，就前后左右上下的移动，还有它的转动，它可以旋转，它可以旋转。那它也可以2颗之间互相在震动，它之间的相对位移的震动。好，那接下来我们就要仔细讲这3个东西。So now, this is really important that for equipartition of energy, because each degree of freedom represents certain energy value. All right, so it's called equipartition of energy, and it will be extremely useful for statistical thermodynamics. So that's the reason why we need to talk about that here. So now, firstly, the most easier one, the most easy one, easiest, simplest is translation. Translation. All right. So the translation easy. X, Y, Z, right? So the mean square speed v square bar. All you know that they are related to kinetic energy, right? Half mv squared. So the v square is you can see that as a vector. The vector containing vx, vy, vz component. Okay, so the v square means that you can see that this is vx square, vy square, v2 square, vz square. Okay, sorry, and sum it all together. Now, why we call that equipartition? It is because there no preference of the direction. So all the direction has equal possibility. So each of them, the equation can be writing down 1/3. And each of them equal to each other. All right. So because no preference direction, 3 direction, they have equal possibility. So 1/3 for each. All right. So the mean kinetic energy per molecular, of course, is half mv squared equal to 3/2 kT. Yeah. And each kT, each component can be seen half mv x squared equal to 16 mv squared, half kT. Okay, so you can imagine that each degree of freedom has half kT kinetic energy. And you can see that there are 3 degree of freedom for translation of the molecule. And each of them has half kT energy. So it's called equipartition, just like the same value for each degree of freedom. If you have that degree of freedom, you own that kinetic energy. 好，我们要讲的是等差距吗？的能量。我们先讲最简单的移动的，移动的想象一下就是速度的向量，还有 x y z 的分量，这几个分量，这个速度向量的平方的平均的平方就会是 x y z 的分量的平方相总和。但是因为它们没有任何的 preference， 没有任何的喜好，都是一样的几率，所以它们的几率相等，所以它们是1/3的。好，那我们又知道1/2 mv 平方等于3除以2 kT， 所以我们可以等同于一个方向的自由度就会分到1/2 kT 的能量。OK， 那这边有3个自由度，所以是1/2 kT 乘上3除以2 kT。All right, next hour I will give you more detail about the rotation part. All right, see you later. Thank you. Này,
请问这个是大线机90度，然后这个转一圈，所以就刚好这个整个半球这样。
对我的意思，对，但我的意思是说，为什么不是要记一整个球？我有点忘记为什么，
就只要算半球，
它只要算半球就好了。哦，没有，我在想这个是，我忘记了，因为我，如果今天他撞到这个，他只需要 strike， 他只需要半边，他不用考虑对面撞到他吗？有点，还是他本来就是考虑半球？
也是因为上半球是上面往下的动量，
对，
下半球是下面往上，
所以要分开计算。
对，所以应该要分开计算，而且
啊，
它这个计分是要算
pressure 那个嘛，
所
所以它不能把这个一半啊，对， 谢谢你们两个都是讲这样，那再来一次啊，再那个，好啊，很棒，感谢你。来，那我就把这个复制下来好了哈，可以吗？
好
啊，剪下，贴上，这样，OK。所以，嗯，所以通量是指说它只考虑它，哦啊，我对啦，通量是从这边通过去嘛。
对
那如果今天你在考虑的话，那就 double 了。
对对，
对，有正通量跟负通量啊。对对对，谢谢你，好，感谢你。那就再挑个礼物吧，太棒了，谢谢你。那怎么写呢？嘿，
比较笨一点，
没有，
但是我觉得他讲的其实蛮对的，只是用老师里面的那个，
嗯
就是讲到说，其实刚刚跟你们讨论也蛮像，他就是说，如果今天考虑到下班时的话，
嗯
如果以分子的角度来讲的话，
嗯，
他会跑掉，
跑掉。
就是怎么讲？我觉得老师看的好，
好，我看一下，
预估
没问题。嗯，然没问题。有些时候呢，to the geometry constraint problem. We are usually concerned with molecular toward the surface if we think of an extra plane, for instance, the positive will move toward it, while those below the plane, the negative will move away.
还是不能这样子表示。
As we only care about molecular. 诶，这个他讲的有一点，我觉得也不是到很好。其实这个应该叫做通量的真实定义。所谓的通量，你还记不记得？如果今天我们要看，我们讲水好了，水管，我们这个水管水通过去，我们就看就是它是我们要考虑的是这样的通量跟这个通量。如果今天这个通量比较少，这个通量比较多，这个水就会往这边流。对，我们之前讲这种水管的概念是这样，那其实 molecular flux 也是，它也是讲通量，所以它是在讲这个东西打到这个方向过去。如果今天我们这个用就两个一起算的话，那就没有方向性，它就没有正通量或负通量这种感觉。所以说，刚刚他们讲的蛮对的。那这个东西，我感觉他的解释的反而是这个东西，这个，哎，我觉得他是解释这个，我觉得啦。而且他说，
哎，这是老师应该是上课蛮多个档案在这个，
对啊，对啊，对啊，
大概有18个。
哦，是吗？in the negative 是这种，我就觉得他这个有点怪，什么叫做 move away 的，就有点不太懂，这我就有点看不太懂。不过感谢你使用它，它还好用吗？
但某部分
某部分可以，好，谢谢你，谢谢。但是我要怎么写呢？这有点难写。做吧。像刚刚这样的。写呢？ Hello, welcome back. Thanks again for these the two students. They really had good a good at logic and the definition of the physics. Really good. They mentioned us. They mentioned that they remind me that the fundamental fundamental definition of molecular flux. I believe this is not your first time to hear flux term, right? The flux, typically when we talk about the water pipe, when you talk about the water flow in and sometimes it will flow out, and then flow in and out is a flux. So the flux can be positive or negative, right? So which means that in and out nature. So, which means that you can imagine that this is a container that you have water fill in. So the flux was into the container. But if the water may have another flux outward, flow out of the container, you need to see net flux, right? So the flux has in and out nature. So it should be positive or negative for a container. So if we consider both sides is do the integration as a sphere all the direction, which means that there's no sense of in and out, because in and out you consider both of them. So there's not correct, not match the definition of the flux. Okay? Maybe you will ask why you consider all direction, because now we talk about the direction to hit that area, all the direction, and the possibility of the particular direction here. So we need to consider all direction here. But now for the molecular flux definition, we only need to consider one side of it, because we need to consider this is out and this is in. Okay, so the reason why we only consider half of it is because of definition of the flux. Okay, thanks. These two students remind me this important definition that I forgot. 中文讲一次，就是说呢，就是说，我刚刚忘记了通量这个的这个定义，其实是在讲一个东西的进跟出。我们应该不是第一次听到通量这个词，我们在可能想过就是一个水管，它的这个出入口进的通量跟出的通量是不一样的，有的时候出的比进少，那这样子，出的比进多的话，那这个容量就会变越来越少，越来越少，有这种感觉，就是我们之前学到的通量是这样的意思，所以 molecular flux 也是一样的感觉，也就是说我们要去看这个 particle 是有 molecular 是出去这个地方还是进来这个地方，所以有这个 in and out 这件事情。那如果今天我们考虑了全部的 direction， 你在这边的积分考虑了全部的 direction 的话，表示说我们 in and out 全部绑在一起，那这就没有通量可言了。OK， 所以说我们只考虑一半，可以考虑进的。那如果是另外一半的话，就是考虑出的。不对，这边是考虑出的，另外一半是考虑进的。OK， 那所以这就表示说我们只能考虑一半的球。那可能同学会觉得说，那为什么这边要考虑全部？这边不是考虑通量哦，我们这边考虑是几率问题。我们这边考虑的是这一个方向在全部方向的几率问题，所以当然要考虑全部的 sphere。那这边不是，这边是考虑进跟出，所以只能考虑一半。这样，感谢两位同学给我这样解释应该蛮合理吧？哈 ，OK 哈，谢谢大家。好 ，Thank you, good. I don't know, maybe this simple foundation concept. Of course, I learned that before. I already learned that before. So I naturally just plot this sphere, but I forgot. Because I haven't been asked for a long time. But actually, nobody asked me. I asked myself when I do the lecturing. So this is really interesting. So you actually learn things and remind yourself by teaching. So teaching is quite a nice activity for you and everyone. Yes, good. Next one. I hope. Oh, not muted. Good. All right, so let's continue. Molecular. Degree of freedom. So this is really interesting. And I also open another bonus later. Okay. Bonus opportunity later. So please be careful. Now I'm talking about equipartition of energy continued, and we're talking about a diatomic molecular. Then diatomic molecular means that two particles connecting by the spring. And let's take a look. I will give you an answer first. There are 7 degrees of freedom in total. This is the answer. And let's count one by one. So the first one is that the diatomic molecular has X direction, degree of freedom 1. Y direction, degree of freedom 2. 3. Z direction, degree of freedom 3. And then rotational degree of freedom. Rotational degree of freedom, rotating about X axis. The fourth one, and rotating about Z axis. The fifth. And then kinetic potential energy is a vibrational degree of freedom. Kinetic means that how fast it is. And potential energy is that how the spring squeeze so that they has the potential to move back, repulse. So 1, 2, 3, 4, 5, 6. Come on. 7. 7. Okay, so this is 7. I believe you feel strange. Why there's no not 8? Why? Why not this one? Why we cannot rotate about y-axis? Can you answer me? Can you answer for this question to everyone? Why the rotation about y-axis absent? Why? I just skip this. Why? Why x and y is okay? Sorry, xz okay, but y is not okay for this moleculars. Anyone? You can imagine that this diatomic molecular is kind of a pan, and it can rotate x, and rotate x, right, x, and z. How about y? So can you explain why y-axis rotation is absent here? Not the degree of freedom, please.这是转动 ，this is rotation。所以你在 y 转的话会怎么样？就没差，对不对？你的意思是这样，就没差嘛，对不对？没错，答对了，谢谢。So there's nothing changed in the y direction rotation. You see x, okay, z, okay, you see that moving, right? But y rotation, you see nothing, right? They are the same. So the state is still the same. Very good. So Chinese, English, good. So both of you can just like come down here and write down your number, and you can pick your gifts, please. So do you understand what I'm talking about? So come down, please. So you can imagine this is a pan of is a molecular, and molecular rotate x. Okay, you can see that rotating. Z rotating. Yes, you can see that. But y, it doesn't change the state. You see, y rotation has nothing. Okay, so you can write down the numbers here. Right. So only x and z rotation can be seen as moving, but y doesn't change. Y-axis has nothing to change. So pick up the gifts. Thank you. Right, very good. And this is the friend with light. 这么好，感谢感谢。哇，还有很多差不多，这个是那个什么消毒的好，哎，那这个沙后面这个，对，好亮，你可以把它动起，确定。好，谢谢，耶，很棒哦。卫生筷，方便，来做成手状棒的。还有什么？就是你说，就是那个为什么卡夹？然后下次可能会有杯子哦，是瓷杯哦 ，ceramic cup，very nice。好 ，OK，Thank you. So continue. 1 degree of freedom associated with every form of energy expressible in quadratic form. Of course, half mv squared, right? Half kT, good. The total energy of a molecule is half kT times F7, right? So you can see that each degree of freedom providing half kT energy. So when you have 7, you can have 7 kT divided by 2. All right. So the internal energy of gas U equal to N times epsilon bar, half F NKT or half F MRT. All right. So that's equipartition of energy means. 好，刚刚讲到就是说，要讲什么？好，我要讲的就是每一个 degree of freedom 都会有自己的kT 嘛，对不对？哈，那所以 x 方向的移动、y 方向的移动、z 方向的移动可以。不好意思，我忘记讲，我们现在讲的是两颗原子的分子 ，OK？ 那今天在 rotation 的方向的话 ，x 方向可以转，你可以看到它正在转动，这整颗在转，没有问题。或是 z 方向这样转，应该没有问题。但是 y 方向没有的原因，是因为感谢刚刚2位同学解释，就是说它自己在转，它本来就已经在这个方向了，然后它自己在转，你根本看不出来它有在转，所以它根本没有 degree of freedom 在那里，它的状态都一样。它在这样子的转动方向上，它的状态都维持不变，所以它这不算是一个 degree of freedom。然后还有弹簧的 kinetic 动能跟位能。压缩动能跟位能的degree of freedom， 所以呢，有7个，就是2/4 kT 乘上7，就是它的总能量，这样子。OK，next one. Next one. So this is really useful for us to determine certain material properties that we actually can be measured in reality. For example, specific heat capacity. So CV equal to partial U over partial T at constant V. So we just obtain U, right? So the U will relate it to the degree of freedom. So F2. RT equal to F2 R. Okay, so Mayer's law, Cp equals Cv plus R. So we can also say this is F plus 2 divided by 2 times R. Okay, so the ratio of specific heat is gamma. Gamma Cp over Cv equal to F plus 2 over F. Okay, no problem. So now, this is really interesting. So this is we obtained by the degree of freedom and for ideal gas. And now for a monoclinic gas, what does that mean? What does that mean? Is helium, right? Or argon, okay? And their actual value, see table 11.1 in the textbook, you can find that helium has the gamma ratio 1.66, 1.67. It can actually be measured, okay? This is real value. And we found that monotonic gas, because there's no rotation, no spring vibration. So it only has XYZ translational F equal to 3. So CV equal to this one, CV equal to this one, and gamma equal to 5/3. 3 plus 2 divided by 3, right? So 1.67. Good. So which means that the theoretical value match the experimental value. Good. How about diatomic gas? Diatomic gas like H2 and O2, right? 1.4, 1.4. Okay. So you see that for diatomic gas, F equal to 7, right? We just talked about in the previous page. It should be 9/7. It should be 1.28. Okay. It doesn't match the experimental value. And if we just try that. We try 5. Five become 1.4. Okay. It matched accidentally. We don't know why. With diatomic gas should be 7, right? But we just randomly try 5. It matched. So the concept we learned in the previous page is wrong. We don't know, right? So actually in chapter 15, we will tell you why. And actually in the room temperature, two rotational two degree of freedom are locked. I shouldn't say rotation. Rotations, well, it's another story. But I'm just saying that two out of 7 degree of freedom has been locked at room temperature. Okay, so which means that degree of freedom may not always available for you. It should depending on room temperature, and they require quantum mechanical description to tell us why. Okay, so that's it. 好，我们刚刚讲到 degree of freedom，然后我们就可以让它算出我们的 internal energy， 就是degree of freedom 的数量乘上kT。好，那我们就可以把它连接到真实的材料参数喽。例如说 CV， 这 CV 呢就算出来是FR。好，然后呢我们的 CP 又可以照样算出来，用 Mayer's law 算出来，然后我们就可以算出它的 gamma 的这个 ratio。OK， 这 ratio 会是 F+2除以 F。好，那这时候我们就会看理论值跟真实值有没有相同。单原子的只有 XYZ 3个 degree of freedom， 它们不能 rotate， 因为它只有一颗球啊，它没有 rotate， 它们也不能震动，它只有3，就算出来它的 gamma 是 1.67， 就跟真的答案是实验值答案是一样的，很好，做得好。但是呢，我们如果是 diatomic 的话是7，就算出来是 1.28， 可是真实的量测发现 1.4， 有差距耶，差很多，不符合我们的理论。难道我们错了吗？那我们就随便乱 try 5好了，结果发现5的答案就对了。刚不是说7吗？怎么现在变5才是对的呢？原来是有2个被锁住了，在 room temperature 下被锁住了。 degree of freedom 有时候会被锁住，要看你的温度的开启的状态。所以说呢，这必须要有量子力学的观念去帮助我们解释。我们在第15章会解释到。Okay, next distribution of molecular speed. 啊，每次到这时候就开始觉得好累，就开始觉得好，我不想讲了这样。啊，不行，我们要坚持下去。好，加油。本来想要分享什么，但是好像最近没什么东西好分享。哦，对了，我昨天买了 Switch 了，终于买了 Switch，是我的生日礼物。然后，不是昨天了啊，最近。然后昨天就买了，但是我已经很久没有接触电动，所以就电动玩具了，所以我就开始在那边弄，我弄了1个多小时，然后都没办法买线上游戏。我后来才发现，原来台湾不能买日本的就是任天堂的游戏，大家应该知道这件事。我看到有人在点头，他觉得我这个人很菜，这么大家都知道的事情，这样我不知道，对我真的不知道，我就弄了。在台湾我还选台湾，老实的选台湾，然后就不能买。我想说这到底在干嘛？然后后来去上网查，哦，原来去选什么香港、日本、美国才可以买游戏，这我在搞什么？但是，所以我昨天弄了很久，都没玩到游戏，太令我生气。好，总之现在啊，其实我 PS4，我从2015年我买我的 PS4，我跟大家讲，我玩 PS4 的次数，这十年来应该不超过100次，真的不超过100次。对，就这样放在那边呢。然后我现在都是会看到游戏我就买下来，但都没有玩。然后就例如说呃，例如说火影忍者的疾风传啊，我买了我都没玩过。然后还有什么？哦，然后海贼无双4我也买了，我也没玩过。唉，真的很难过。对，就是现在就是年轻的时候，小朋友的时候，就是想要买电动玩具，然后没钱，但爸妈不准这样。现在就是买了，然后又没时间玩，真的是人生的悲哀。好，就是这样。好了，就这样，继续下去。Distribution of molecular speed. So, molecular speed, right? We talk about that. So the distribution of molecular speed all related to the possibility. So possibility density function. Okay, FV. It must be related to FV. So it is not. Actually, we're going to see what is FV looks like. Remember the FV looks like this, right? We just say it looks like that, but we haven't actually write down the mathematic expression for this. So now we are going to get that what FV looks like. All right. So now let's go back to the origin. Velocity. Velocity is particles velocity, and this V here is vector because this is upright form, right? The small v with italic is the magnitude of velocity. So the relation is that the absolute value of v vector equal to v. All right, that's it. And And later we will determine Maxwell-Boltzmann distribution in chapter 14, right? And we will determine by the particle amount energy level, which is different from this one. All right. So we just talk about, when we talk about just speed without the energy level concept. So these two are different. We just mentioned that there are several different distribution. We will introduce in this lecture. Okay. So now let's take a look. FV and FV, well, they are different. Small fv and capital F. This is capital F. This is different, okay? So please be careful. In the textbook, the fractional number F, okay? The number, they are different. They are really, really different, okay? In our book, they just write it down like this, but never emphasize it. So it will mess up, will make confuse all your seniors and myself when I was studying this. Okay, so you see that irreversible direction. So later you will see the FVdV and capital vector VdV. And this one is the fractional number. And irrespective of direction, because V is value. But now, capital F is a number. Okay? So fraction is 0 to 1. The number can be infinity. Okay? And V here is a vector. So considering direction. Okay? Here is magnitude is irrespective of direction. So this is really important. So important. Okay? From now on, we will use these two things. And you need to notice the difference. OK， 好，我们要讲是分子速度的分布，其实就是我们的 FV 啦。哦，刚刚不是说它长这样吗？但是我们没有写出来啊，我们要把它写出来。它到底长什么样子？它的数学式是什么？这时候我们就要回归到原子的速度 ，V 是向量啊，粗体、正体、斜体就会是它的值，所以呢，我们的绝对值向量就会等于它的值。OK， 斜线 V， 好，这边是要请大家注意的。接下来呢，Maxwell-Boltzmann distribution 是另外一个 distribution 是分布啊哈，它在第14章会教，跟这没有关系，它会跟 energy level 能阶有关。现在这个跟能阶没有关系。OK， 所以要请大家注意一下。接下来呢，我们会有2个不同的东西，在课本上就直接写上来，没有给你强调它们之间的差距。那我这边把它拿出来，重点讲一下，就是斜线 F 斜线 V， 不是斜体 F 斜线 V 斜体 V， 它是 fractional number 哦，是0到1哦，它的答案是0到1哦。然后 V 是因为它是值，所以它不管它的方向。当然这个 V 是向量，就有管方向咯。然后这个大写 F 是 number 哦，它可能是0到无穷大哦。小 f 是0到1之间哦，所以这2个是非常大的差别，所以要非常非常小心，等一下会用到。Right. So let's discuss the Maxwell-Boltzmann velocity distribution. You see, Maxwell-Boltzmann velocity distribution and Maxwell-Boltzmann distribution are different. Okay, so one is chapter 14, the other is chapter 11. So be careful about this. Okay, and now we'll talk about in a dilute gas, we assume binary collisions. We assume that each time stage, two particles bump together. Bang, 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 bang. All right. So input velocity for particle 1 is V1. Input velocity 2 for particle 2 is V2. So 1 and 2, right? Bump together. And with the output velocity V1 plus V2 plus, you can always find this, right? No problem. So there, this case, number of collision should be capital F times V1 times capital F times V2. Okay, so number of collision occur between molecular 1 and 2 per unit time is this one. But don't forget the A here. The A here is the scaling factor. Okay, you see this is a number of collision, right? So if you have a bigger container, you will have bigger number of collision. So A is corresponding to the container. Okay, so just a random constant. We can say constant of proportionality. Basically, just correlated to the system size of the system. Okay. Now we can always find a mirror condition we call inverse collision, which means that it 1 and 2, it inputs by V1 plus, input by V2 plus, and output V1, output V2. This is a 100% mirroring, right? You can always find that, of course. And their case is F V1 plus, F V2 plus times together. So this is the number of collision for that. Of course, for this container, they have A plus container scaling factor. Now, because if we treat them as the same container inside the same container, so we can assume that they are in the same container, A and A plus can be cancelled. And also because they are all mirroring, so all the velocity appear are all the same. So which means that their number in the same container should be the same. Okay. So now let's see two functions times together equal to each other. So typically when we want to know more thing about this, we typically do some mathematical transformation. We don't like multiplication, we like plus. So we take natural log on it. Natural log on it, natural log f v1 plus natural log f v2. Natural log f v1 plus natural log f v2 plus. Still the same, right? So we just, we don't like times. This is too complicated. We make it natural log become plus. Everything become easier later. Okay, you will see that. So you can see this is 1. Question 1. And we can give us a constraint. What is a constraint? The constraint is that constraint is conservation of kinetic energy. So because the bumping are energy conserved, so half mv square is a kinetic energy, right? V1 square, half mv1 squared plus half mv2 squared need to be the same, right? But now, I mean, equal need, sorry, again, sorry. I should say half mv squared is a kinetic form, right? Kinetic energy form. So half mv1 squared plus half mv2 squared need to be equal to half mv1 plus squared plus half mv2 plus squared. So these two cases need to be the same. And we cancel half m. So become v1 squared plus v2 squared equal to v1 plus squared plus v2 plus squared. Okay, so this is a constraint that we need to satisfy constrained by physics, by reality. So now here, it can tell us, and we also know that v dot, this is vector, right? Equal to v squared absolute value. So it become v squared. All right. So you can see that v squared, it can tell us, this can tell us, okay, v1 dot v1 plus v2 dot v2 equal to plum. Okay, this is second equation. So the second equation comes from reality, comes from physics law. Okay. So combine 1 and 2. You see that there's a function that can make the the input velocity times together and similar to the natural log. Okay, so you can see that they so you can see that there's a function f that can make v1 after the natural log look like dot to itself. Okay, so you can examine this two equation. A possible FV should be looks like this. FV should looks like exponential V dot V. Okay, so only if the F looks like exponential V dot V can make this satisfy these two equations simultaneously at the same time. Okay, so the FV must looks like equal to the exponential and V dot V. Of course, you know that because we have the equal signs to connecting left and right, so we definitely has a constant need to be considered, right? And now the alpha here, I give you a minus sign here. Don't ask why, because we know the answer later. But we just say we can assign positive alpha or negative alpha. It's okay, right? So we're just saying that there are two undetermined parameters here, alpha and A. So this is capital F things. We can also say small fv also in this form. Of course, their A and alpha may not be the same, but they must be in the same form because they are similar. Their nature are similar. Okay, that's it. 好，现在我们要讲啦。我们刚刚介绍过 F 跟大写 F 跟小写 F 的差别，那我们就来看，我们想要知道它长什么样子。现在来讲 Maxwell-Boltzmann velocity distribution。好，我们要假设啊，两颗球撞在一起，每一次都只有两颗球撞在一起，两颗球撞在一起，两颗球撞在一起。好，那我们有假设它入射 V1， 入射 V2， 出射 V1 plan， 出射 V2 plan。那它们要产生这样子的状态，会有几个呢？在这个 container 下会有几个呢？那它就会是它的 F V1 乘上 F V2。你看哦 ，F 是个数嘛，对不对？所以你看这边是格数，是 number， 对不对？好，那接下来我们乘起来以后就是它的个数咯。哎呀，是它的个数。但是呢，今天如果它的容器越来越就是2倍大，它的几率也会变2倍，次数也会变2倍嘛。那3倍大就会是3倍，所以这个阿尔法是 A， 这个 A 或阿尔法它就是跟 size 有关啦，就在这边写在这里。那我们一定可以找到另外一个对称的，是入射 V1 plan 入射 V2 plan 出射 V1 出射 V2 的这样子的碰撞情形。那这样的情形呢，一样是这样子的算法。那它的 alpha plan 是它的容器。假设我们俩的容器是一样的，我们就消掉了。这样子的镜像的 case 出现的速率都是一样的，都是这4个，它的几率当然就会是一样，次数当然就会是一样，然后它们就会相等。好，那相等完以后，它是用乘的，我们不喜欢乘，我喜欢加比较简单，所以我们就取一个 natural log， 让它产生第一个式子。那解不开来怎么办呢？我们再去看有没有其他东西可以帮助我们解题。有的，物理上它们的动能会守恒，所以呢，1/2 mv 平方下左半边跟右半边加起来要相等，所以1/2 m 消掉以后会变成 v1 平方 v2 平方加起来会等于 v1 plan 平方加 v2 plan 平方加起来。好啦，那这时候 v2 就是 v 的平方又可以是什么？可以看成什么 ？v 打 v 就是向量的内积，自己乘自己。好，那所以说我们综合以上，我们就可以说 v1 打 v1，v2 打 v2 会等于 v1 打 v1 的 plan 跟 v2 plan 加打 v2 plan。好，这两个式子观察一下，我们就会发现，只有一种 f 的形式会满足上跟下，也就是 exponential 代入进去的话，它做 natural log 的 v 打 v 就会跑出来，然后相加，对不对？所以说它一定要长这样子。好，那长这样子的话，我们就写出来 FV 会等于 A1 负阿尔法 V 打 V。这个负阿尔法为什么写负？是因为我知道答案，但实际上你要写阿尔法也可以，然后直到最后就会多一个负号，没关系。总之 A 跟负阿尔法就是因为它的等号，它如果有这些 A 啊什么阿尔法，它都会消掉，所以我们不能说它不在啊，所以我们还需要把它写进去阿尔法的值。我们等一下要去求它 ，OK？ 那接下来有大写 F 的、小写的 F 的也可以这样写，只是它们的 A 跟阿尔法可能会不一样而已。就这样。好 ，Right. So next, so consider again, mv dv is the number of molecules in the speed range of v2, v plus dv, irrespective of direction. Okay, so you can imagine that V and V is a magnitude irrespective of direction. Okay, and NV of course is a number. Okay, so your NV dV equal to 4 pi V squared F d by V dV. What does that mean? 4 pi V is the surface of area, surface area of the speed sphere, right? Okay, so remember this figure, right? So because we are irrespective for direction, so all the direction can be should be considered. Okay, so 4 pi V squared and FV dV. All right, so this should be 4 pi V squared AV minus alpha V squared. All right, so now this is NV dV. Total energy in the container is 3/2 NKT. So we times half mv squared times all the number of molecular in all the direction. And from 0 to infinity speed, it should be equal to each other, right? So this m here, we can manipulate a little bit about this to make m to the left hand side and n to the right hand side. This is the m. This is the m. Okay. And what is m? This is interesting. M here can be regarded as 0 to infinity for all the speed number. So actually, it is m, right? So if you integrating all the velocity, because this is a number of molecular within this range, and you consider all of them, of course, it becomes the total number of n, right? So I guess I don't have time, but later, next week, I will continue to solve this problem, and you can get the distribution like this in next week. Thank you very much. If you have any questions, just come here. See you next week. Thank you. Do my